Less than 5 hours before splashdown, the crew of Apollo 13 released their service module and photographed this. An entire exterior panel was missing. But the hole is not the strangest part. The strangest part is that the most probable cause was created just over 2 weeks earlier, inside an oxygen tank, during an 8-hour ground operation. Its temperature display could show no more than 85 degrees Fahrenheit. The heater assembly inside could have reached about 1,000. The readout was off scale. The heater current clue went unchecked. And now, almost 200,000 miles from Earth, the only spacecraft that could survive re-entry would have to be turned off. We will begin where the crew's story almost ends, follow this evidence backward into the tank, then carry every consequence forward until the photograph makes sense. Apollo 13 was 3 specialized machines traveling as one stack. Odyssey, the command module, carried the crew and the heat shield that could enter Earth's atmosphere. The service module supplied oxygen to fuel cells, and those fuel cells made electrical power and water. Aquarius, the lunar module, carried landing batteries, oxygen, and a descent engine. It was meant to separate and descend to the moon, not bring 3 people home. Before the accident, the planned landing trajectory had also taken the stack away from a path that naturally returned to Earth. To survive, these 3 machines would have to trade jobs without spending the one function needed at the end. Watch 5 identities as they move: cyan oxygen, amber electrical power, blue water, magenta carbon dioxide, and a green trajectory. They are not 5 separate emergencies. A choice that protects one can consume another. The rescue is the changing shape of that single circuit. Oxygen Tank 2 had once been installed on the Apollo 10 service module shelf. During removal, the shelf's front edge rose about 2 inches before its support fixture broke and the assembly fell back. The review board judged direct tank damage from the incident unlikely, but it may have disturbed the fill and drain assembly. Later at Kennedy, the tank would not empty normally. The workaround was an 8-hour boil-off using heaters on a 65-volt ground supply. Their thermostat switches were rated to open at 30 volts. When they tried to open, the contacts probably welded shut, holding the heaters on. The temperature gauge reached 85 degrees and could show no higher. Inside, the heater assembly could have reached about 1,000, degrading Teflon insulation around the fan wiring. A ground team saw a completed D-tank and a bounded display. Neither observation revealed what the wire insulation had endured. The tank passed onward carrying a hidden condition. At 55 hours, 53 minutes, and 20 seconds into the mission, Jack Swigert switched on the tank fans. It was routine. Within seconds, the electrical system registered brief disturbances. Damaged insulation probably allowed arcs in the fan motor wiring to ignite Teflon. Pressure climbed inside the tank. About 93 seconds after the fan started, the tank lost integrity. Escaping oxygen pressurized Bay 4 and ejected the exterior panel. A bang and warnings arrived almost together. Telemetry vanished, returned, and contradicted itself. 27 seconds after the physical failure, Swigert called Houston. The famous sentence reported a problem. It did not explain one. Between the first power transient and that call, pressure rose, sensors failed, oxygen flow to fuel cells 1 and 3 fell, and the spacecraft accelerated in 3 axes. The crew and mission control could see only disconnected symptoms arriving through damaged sensors. Suspense here is not ignorance of the ending. It is the gap between physical reality and what a human system can know in time. At first, the data looked like instrumentation trouble. One oxygen quantity reading jumped high, then low. A bus voltage recovered, then fell again. Fuel cells and buses failed without announcing one cause. The crew even tried to close the tunnel hatch, reacting to a possible cabin leak. 13 minutes after the bang, Jim Lovell looked through the window. A cloud was streaming into space. That observation reorganized every reading. Oxygen was physically leaving the spacecraft. And oxygen here was not just air, it fed the fuel cells. Lose it, and Odyssey also lost its normal electricity and newly generated water. Tank 1 was losing pressure. 2 fuel cells went offline. 1 electrical bus collapsed, and the other weakened. Commands that might fix a valve or sensor could not repair an open path to space. The vent transformed uncertain telemetry into a finite supply. Every powered minute in Odyssey now consumed a reserve the crew would need at Earth. The rescue did not begin with an instant 15-minute countdown. For more than an hour, crew and controllers diagnosed the loss, protected the remaining fuel cell, and considered a lunar module lifeboat. Only when the final command module margin fell to roughly 15 minutes did that idea become a race. None of the activation checklists matched this damaged, still docked configuration. Mission Control cut away unnecessary steps and called up specific pages. Aquarius had to provide oxygen, cooling, communications, and a live guidance platform. Essential functions crossed the tunnel while Jack Swigert remained in Odyssey, completing the shutdown. The aim was not merely to turn on the lifeboat, it was to stop spending the future. Its guidance platform inherited an alignment from Odyssey through a manual procedure because the usual sequence assumed two independent, healthy spacecraft. Every shortened step solved an immediate need while protecting lunar module consumables and command module batteries. Aquarius was now the spacecraft's live heart. This is the central paradox of Apollo 13. Odyssey was the only machine with a heat shield. It was the only place the crew could be during atmospheric entry. Yet every minute it stayed alive consumed the batteries reserved for that entry. So the spacecraft they most needed had to go dark. Its cabin cooled. Moisture condensed. Systems that had never been designed for a long cold soak waited without power. Aquarius inherited life support, guidance, and control, while a small amber reserve remained sealed inside Odyssey. Turning a spacecraft off is usually a loss of capability. Here, darkness was the mechanism that preserved it. The shutdown also created new risks, or equipment cooled for days, and condensation gathered near electrical systems. Clocks, guidance, and communications would later have to return in a new order. The entry batteries were not simply locked away. Some had already been depleted. Aquarius would eventually charge them from its own limited supply. The lifeboat borrowed time from the landing vehicle to preserve the reentry vehicle, then repaid part of that debt before separation. Now the forensic chain can close. The shelf incident was recorded, but the review board did not call it a proven ignition cause. The detanking problem was known. Its thermal consequence was not. Ground heaters were 65 volts. Thermostat switches remained rated for 30. The gauge reached 85 degrees and went off scale. The heater assembly may have reached about 1,000. Teflon insulation was damaged in oxygen. Weeks later, a routine fan command supplied the final trigger. The fan did not create the history, it revealed it. This is why the accident cannot be reduced to one careless person or one bad switch. Each decision fit a narrower model. The drop appeared harmless. The detank succeeded. The readout hit its upper limit. The fans had worked before. Danger existed in the interaction between hardware history, voltage compatibility, instrument limits, Teflon insulation, and supercritical oxygen. The review board revealed that interaction afterward. Survival still required a path home. A normal mid-course correction had moved Apollo 13 off free return and onto its landing approach. Pointing at Earth was not enough. The stack had momentum, limited propellant, and the wrong engine for the original plan. 5 hours after the accident, Aquarius fired its descent engine, bending the trajectory into a loop around the Moon and toward Earth. After passing behind the Moon, a larger burn called PC+2 shortened the return. One burn restored a rote, the next spent propellant to buy time. Every correction traded one margin for another. Debris obscured stars, so the crew checked alignment against the sun. Lunar shadow later made stars visible again. The first lunar module burn lasted roughly 34 seconds. PC+2 delivered about 860.5 feet per second. It moved splashdown from the Indian Ocean toward the Pacific and reduced the time that batteries, water, and filters had to last. The Moon was not a scenic flyby, it was the fixed body around which every resource calculation bent. Aquarius had been designed for 2 people for about 2 days. It now had to support 3 people for roughly 4. Oxygen was comparatively abundant, but the other margins were coupled. Turning equipment off saved battery power, yet water was needed to cool the electronics that remained. The crew cut drinking water to about 6 ounces per person per day. The cabin fell to about 38 degrees Fahrenheit, and condensation formed on the interior surfaces. This was not an ice cave. It was a dim, damp machine operating far outside its intended duration. Meanwhile, 3 bodies added carbon dioxide to a cabin designed around 2. Controllers drove electrical load down to roughly the 350 to 400 watt range. Water served both bodies and electronics. Stored water and fuel cell water were separate reservoirs, although the accident connected their consequences. The budget was one duration shared by bodies and machines. Saving electricity cooled the cabin, and by reducing waste heat, also reduced cooling water demand. The crew had enough command module lithium hydroxide cartridges, But those cartridges were square, and the lunar module's environmental system used a round interface. The scarce resource was not filter material. It was a compatible path for air. On Earth, engineers built and tested an adapter from the same flight materials available on board: a plastic bag around the square cartridge, cardboard from a procedure cover for support, tape for seals, a suit hose to drive airflow, and sock material to block a bypass. The cartridge never became round. The airflow was rerouted through it. That is the difference between a clever prop and an engineered interface. Mission Control built and tested the assembly, then dictated construction to the crew. Carbon dioxide partial pressure had risen to nearly 15 millimeters of mercury. With the adapter operating, it fell below 1. Duct tape mattered, but tape was only one component. The real invention was a verified flow path between two systems never designed to meet. Reaching Earth was still not the same as surviving entry. Odyssey had to meet the atmosphere inside a narrow flight path corridor, too shallow, and the capsule could skip away. Too steep, and heating and deceleration could exceed its limits. Small correction burns used the Earth, its terminator, and the Sun as visible references when normal navigation was compromised. Then came the coast. Conserving power was itself an action, punctuated by measurements that might force another correction. The trajectory line was not a promise, it was a protected hypothesis about where the moving spacecraft would meet a very thin layer of air. At about 105 hours, the crew made another short lunar module burn using Earth's day-night boundary as an attitude reference. A final correction near entry nudged the approach back within specified limits. Inventing in the changing spacecraft configuration kept disturbing the path. Mission Control recomputed the future from new tracking. The green line bends, is measured, and is corrected while the spacecraft never stops moving. Before entry, the saved machine had to be rebuilt. Engineers and controllers wrote, tested, and transmitted a new command module power-up sequence in days, a task NASA histories compare with months of normal procedure development. Aquarius also repaid part of the debt. Its electrical system charged Odyssey's entry batteries, roughly 15 hours for Battery A and 3 hours for Battery B. Only then did command after command restore the systems required for separation, guidance, communications, and entry. Each returning load cost power and risked disturbing a cold, damp electrical system. The order mattered because the preserved margin was finite. Odyssey did not simply switch back on. It was reassembled in time. Teams on Earth rehearsed combinations in simulators and on hardware, rejected sequences that drew too much current, and transmitted a procedure the crew copied line by line. Lunar module power supported command module recovery until close to entry. Each relay is an expenditure. The amber line becomes reassurance only after the following load is alive, and the reserve still exists. The temporary spacecraft could now come apart. The service module separated about 4 hours and 39 minutes before entry. For the first time, the crew could see the missing panel beside Odyssey. The image that opened this film now existed, and raised the final uncertainty. Had the nearby heat shield been damaged? After the last transfers, Aquarius was released about 70 minutes before entry. The lifeboat had done every job it could. Keeping it longer would endanger the capsule it had saved. With no normal separation maneuver available, the crew partially depressurized the tunnel. Escaping gas supplied the small impulse that pushed Aquarius away. The vehicles drifted apart nearly 13,000 miles above Earth. Apollo 13 was now Odyssey alone. No lifeboat, no service module supply, and no further way to redesign the architecture. Odyssey entered at about 24,700 miles per hour. A bounded envelope of ionized gas formed around the capsule and blocked radio communication. The expected time passed, then more time passed. No controller could fix anything during blackout. All the previous work had been compressed into this unobservable test. For the first time since the accident, the remaining sequence did not require the crew to redesign the spacecraft while it was happening. Entry compressed days of choices into minutes. The capsule reached roughly 5.2 times Earth's gravity. Its computer used the command module's lift to guide through the corridor. Plasma carried heat away. Blackout extended roughly 2 minutes beyond the normal expectation, long enough for absence itself to become new evidence. Then tracking and voice returned. The forward cover released. 2 drogue chutes stabilized the capsule. Pilot chutes extracted the 3 mains. What looked like an automatic ending was the first time every preserved subsystem had to work together without another workaround. Apollo 13 splashed down on April 17, 1970, 1 mile from its target point and about 4 miles from the recovery ship. Total flight time was 5 days, 22 hours, 54 minutes and 41 seconds. The crew came home because no single solution was mistaken for the whole rescue. Oxygen became power and water. A lander became a lifeboat. A filter problem became an airflow problem. Aquarius charged Odyssey, then let it go. The spacecraft that could re-enter was dark when it had to be, so it could be alive when nothing else could bring them home. That is the photograph's real meaning, not only what was missing, but everything the remaining system learned to become.